Hello there and welcome to Zero Drift, your peaceful passage through the universe. Tonight, we are going to explore one of the most quietly profound principles in all of physics. A principle that answers a question so simple it sounds almost childlike: why can't you walk through walls? And in answering, it reveals something deep and strange about the nature of matter, the structure of atoms, the organization of the periodic table, and the reason the physical world has the solidity and permanence that we take entirely for granted. This is the story of the Pauli Exclusion Principle. It is the story of why no two identical quantum particles can ever occupy exactly the same quantum state simultaneously. It is the story of how this simple prohibition, this single mathematical constraint on the wave functions that describe particles, gives rise to the rich architecture of the atom, the diversity of the chemical elements, the hardness of metals, the structure of white dwarf stars, and the very fact that you are sitting or lying right now on a surface that holds you up rather than allowing you to pass through it. It is also the story of Wolfgang Pauli, one of the most brilliant and most acerbic physicists of the 20th century, a man who deduced this principle in 1924 from patterns in atomic spectra, before anyone had a proper quantum mechanical framework to explain why it was true, guided by nothing more than careful observation and deep physical intuition. And it is the story of the two great categories into which all particles in the universe are divided: fermions, which obey the exclusion principle, and bosons, which do not, and of the profound difference between these two types of matter and its consequences for everything from the structure of atoms to the behavior of laser light. The mathematics of this story involves wave functions and quantum numbers, and the difference between symmetric and antisymmetric combinations of quantum states. These are not simple ideas, but they are ideas that, approached slowly and patiently in the quiet of the night, reveal a structure of extraordinary elegance, a structure that is not imposed on the world from outside, but emerges inevitably from the mathematics of quantum mechanics itself. So settle in, let your body grow heavy and still, let your breathing find its own slow rhythm, and allow the story of the Pauli Exclusion Principle, of the quantum rule that makes matter solid and the universe habitable, to carry you gently towards sleep. To understand the Pauli Exclusion Principle, we need to start with the simplest possible quantum system: a single particle confined to a box, not a box in any everyday sense, but a theoretical construct in which a particle is trapped inside a region of space with perfectly reflective walls from which it cannot escape. This system, known as the infinite potential well or particle in a box, is one of the first and most important exactly solvable problems in quantum mechanics. When you solve the Schrödinger equation for a particle in a box, you find something remarkable. The particle cannot have just any energy, it can only have certain specific, discrete energies, determined by a quantum number n that takes the values 1, 2, 3, and so on. The lowest energy state with n equals 1 is called the ground state. The next state up, with n equals 2, is called the first excited state, and so on. Each energy level has a corresponding wave function, a mathematical function that encodes all the information about the particle in that state. The wave function for the nth energy level is a sinusoidal function that fits exactly n half wavelengths into the box. The ground state wave function has 1/2 wavelength. The first excited state has 2. The second excited state has 3. Each wave function is a different standing wave pattern fitting inside the box. The wave function itself does not tell you directly where the particle is. What it tells you, when you take its square, is the probability density, the probability per unit length of finding the particle at each position in the box. In the ground state, the particle is most likely to be found near the center of the box. In the first excited state, there are 2 peaks of probability, one on each side of the center, with 0 probability exactly at the center. The wave function encodes the quantum mechanical structure of the particle's spatial existence. This is the one-particle picture. Now let us ask what happens when we put 2 particles in the same box. The case of two particles in a box seems like a simple extension of the one-particle case. And if the two particles are distinguishable, if we can tell them apart, label them, track which one is which, then the extension is indeed straightforward. The two particles occupy their own energy states. The combined wave function is the product of the two individual wave functions, and the probability of finding particle 1 at a given position and particle 2 at another given position is simply the product of the individual probabilities. But here is where the story takes its first profound turn. What if the two particles are indistinguishable? The indistinguishability of identical particles is one of the most remarkable facts about the physical world, and one of the most alien to everyday intuition. In ordinary experience, every object is distinguishable from every other object. Two apples may look identical, but they are in different places, made of slightly different arrangements of atoms, with slightly different surfaces and textures and masses. If you look closely enough, or measure precisely enough, you can always tell them apart. But fundamental particles do not work this way. Every electron in the universe is exactly identical to every other electron. Not approximately identical, not identical to within measurement error, but absolutely and completely identical, with precisely the same mass, precisely the same charge, precisely the same spin, with no distinguishing marks of any kind. This is not a limitation of our measurement abilities. It is a fundamental feature of quantum field theory, which tells us that all particles of a given type are excitations of the same underlying quantum field. They are all ripples in the same ocean, and one ripple has no identity that distinguishes it from another. This indistinguishability has a profound mathematical consequence. If you cannot tell two identical particles apart, then swapping their positions must not change any observable quantity. The probability of finding particle 1 at position A and particle 2 at position B must be the same as the probability of finding particle 1 at position B and particle 2 at position A, since probability is the square of the wave function. The wave function itself must either stay the same or change its sign when you swap the two particles, because both cases lead to the same probability when squared. A wave function that stays the same when you swap the two particles is called symmetric. A wave function that changes sign when you swap them is called antisymmetric. These are the only two possibilities that are consistent with the indistinguishability of identical particles. And the choice between them, symmetric or antisymmetric, turns out to divide all the particles in the universe into two fundamental categories. Drift a little deeper now. The room is quiet. The night is holding you gently, and the story is about to reveal one of the most striking facts in all of physics. When you consider two identical particles in a box, say, two particles each in their own energy state, state A and state B, and you require that the wave function be either symmetric or antisymmetric under exchange of the two particles, you discover something remarkable about where the particles tend to be found. For the symmetric wave function, the one that stays the same when you swap the particles, the probability density is largest when the two particles are at the same position. The wave function naturally leads to the two particles clustering together, tending to occupy the same region of space, bunching together rather than staying apart. For the antisymmetric wave function, the one that changes sign when you swap the particles, something completely different happens. When you evaluate the probability of finding both particles at the same position, you find that it is exactly 0. The antisymmetric wave function contains a perfect mathematical 0 whenever the two particles are in the same place. They are forbidden from being at the same location. They tend to stay apart, avoiding each other with a spatial avoidance that has nothing to do with any force between them. This is extraordinary. The two particles are not interacting. There is no force between them, no electromagnetic repulsion, no gravitational attraction, no nuclear force of any kind. They are non-interacting particles in a box. And yet one type of wave function leads to bunching behavior, and the other leads to avoidance behavior, purely as a consequence of the symmetry or antisymmetry of the quantum state. The avoidance is not caused by a force. It is caused by the mathematics of quantum mechanics. It is a consequence of the requirement that identical particles be treated as indistinguishable, of the fact that physics cannot tell which particle is which, and the wave function must reflect this fact by being antisymmetric. The antisymmetry of the wave function is what prevents the two particles from being in the same place, and it does so with perfect mathematical precision. The probability is not small when they would be in the same place. It is exactly zero. Now the next question, the question that determines which type of wave function applies to which type of particle, is determined by a deep result in quantum field theory called the spin statistics theorem. Particles in quantum mechanics have a property called spin, an intrinsic angular momentum that has no classical analog. Spin is a purely quantum mechanical property. You cannot picture it as a ball spinning on its axis. It is an intrinsic property of the particle, like its mass or its charge, that is simply part of what the particle is. Electrons have a spin of 1/2. This means that when you measure the spin of an electron along any axis, you always get one of exactly two values, plus 1/2 times the reduced Planck constant or minus 1/2 times the reduced Planck constant. These two values are called spin up and spin down. The electron is always in one of these two states or in a quantum superposition of them. Photons, the particles of light, have a spin of 1. Pions have a spin of 0. The Higgs boson has a spin of 0. The graviton, the hypothetical particle of the gravitational field, has a spin of 2. The spin statistics theorem, a fundamental result derived from the mathematics of quantum field theory, connects the spin of a particle to the symmetry properties of its wave function under particle exchange. Particles with integer spin 0, 1, 2 must be described by symmetric wave functions. Particles with half-integer spin 1/2, 3/2, 5/2 must be described by antisymmetric wave functions. Particles with integer spin described by symmetric wave functions are called bosons, after the Indian physicist Satyendra Nath Bose. Particles with half-integer spin described by antisymmetric wave functions are called fermions, after Enrico Fermi. Every particle in the universe is either a boson or a fermion without exception. Electrons are fermions, protons are fermions, neutrons are fermions. All the matter particles of the Standard Model, quarks, leptons, are fermions. The force-carrying particles, photons, gluons, the W and Z bosons, the Higgs boson, are bosons. The world is divided, at its most fundamental level, into matter and force carriers, and this division corresponds precisely to the division between fermions and bosons, between antisymmetric and symmetric wave functions. Now we can state the Pauli exclusion principle in its full generality. Since electrons are fermions, their wave function must be antisymmetric under the exchange of any two electrons. And as we have seen, an antisymmetric wave function has the property that the probability is exactly 0 when two particles are in exactly the same quantum state. This means that no two electrons can be in exactly the same quantum state simultaneously. Every electron in a system must have at least one quantum number that distinguishes it from every other electron. This is the Pauli exclusion principle, stated in its most precise form. Wolfgang Pauli deduced this principle in 1924, before the Schrödinger equation existed, before the full mathematical framework of quantum mechanics had been developed. He deduced it from the patterns of atomic spectra, from the observation of how atoms absorb and emit light at specific frequencies, which revealed the structure of their electronic energy levels. He noticed that the patterns of spectral lines made sense only if no two electrons in an atom could have the same set of quantum numbers. He inferred the exclusion principle from the data without yet knowing why it was true. The explanation in terms of antisymmetric wave functions came only later, with the development of quantum mechanics proper. Pauli himself was something of a legend in physics, brilliant, demanding, and famously critical. He was known for the phrase that a particularly bad piece of physics was not even wrong, meaning it was so confused that it did not even rise to the level of being falsifiable. He had a remarkable ability to identify the essential problem in any calculation, and he was formidably productive. His derivation of the exclusion principle and his later prediction of the neutrino, a particle he proposed, must exist in order to conserve energy in radioactive decay, a particle so weakly interacting that he feared it could never be detected, are among the great theoretical achievements of the quantum era. Let your eyelids grow heavier as the story moves to its most beautiful consequence, the structure of the atom, and why the Pauli exclusion principle is the reason chemistry and life are possible. An atom consists of a nucleus, a dense core of protons and neutrons surrounded by electrons. The electrons are quantum particles, and like any quantum particles, they can only occupy certain discrete energy states determined by the quantum mechanics of the atom. In a hydrogen atom, with one proton and one electron, the electron occupies the lowest available energy state, the ground state. But what about atoms with more than one electron? What determines how the electrons arrange themselves? Without the Pauli exclusion principle, the answer would be simple. Every electron would fall to the lowest energy state, the ground state, and stay there. All atoms, regardless of how many electrons they contained, would have the same basic electronic structure. They would all behave the same way. The periodic table would not exist. Chemistry would not exist. The diversity of elements, the possibility of chemical bonding, the complexity of molecules, none of it would be possible. The Pauli exclusion principle prevents this collapse. Because no two electrons can be in the same quantum state, and because the quantum state of an electron in an atom is specified by several quantum numbers, including the energy level and the spin, each energy level can hold only a limited number of electrons. The lowest energy level, the innermost shell, can hold exactly 2 electrons, one with spin up and one with spin down. The next energy level can hold 8, the next can hold 18, and so on. As you add electrons to an atom, they fill these levels from the bottom up, the lowest available energy state first, then the next lowest, and so on. When a shell is full, the next electron must go into the next shell up. The electronic structure of an atom, the pattern of which shells and subshells are filled, determines its chemical properties. Atoms with similar electronic structures behave similarly. This is the origin of the periodic table, the organization of elements by atomic number, which corresponds directly to the organization of electrons by the Pauli exclusion principle. The outer electrons of an atom, the ones in the highest filled shell, are the valence electrons, and they are the ones that participate in chemical bonding. When two atoms come together, their valence electrons can be shared between them, forming a covalent bond. The geometry of this sharing and the energy landscape it creates determines the shape and stability of the resulting molecule. All of chemistry, every molecule, every reaction, every biological process emerges from this foundation. The Pauli exclusion principle is not merely a curiosity of quantum mechanics. It is the reason carbon can form 4 bonds, the reason oxygen can form 2, the reason nitrogen can form 3. It is the reason DNA has the shape it does, the reason proteins fold as they do, the reason enzymes can catalyze the reactions of life. The entire complexity of the living world rests, at its deepest level, on the simple prohibition that no 2 fermions can share the same quantum state. As you rest in the deepening quiet, let the story move to the question we began with, the most everyday and most deceptively simple question in all of physics. Why can't you walk through walls? Your body and the wall are both made of atoms. Atoms are mostly empty space. The nucleus of an atom is roughly 100,000 times smaller than the atom itself, occupying a volume roughly 10 to the negative 15 times the volume of the atom. If an atom were the size of a sports stadium, the nucleus would be a grain of sand at the center. The electrons are not even particles in the classical sense. They are probability clouds, wave functions spread through the space around the nucleus. Given this, why can't you push your hand through a wall? Why does matter feel solid? Where does the resistance come from? The answer is not primarily electromagnetic repulsion, though that plays a role. The fundamental answer is the Pauli Exclusion Principle. When the electrons in your hand approach the electrons in the wall, they are approaching other electrons. And electrons are fermions. No two electrons can be in the same quantum state. As the electrons from your hand try to occupy the same region of space as the electrons in the wall, they would have to occupy the same quantum states that are already filled by the wall's electrons. The Pauli Exclusion Principle forbids this. There is no available quantum state for your electrons to occupy in that region. As the electrons are pushed closer together, the exclusion principle forces them into higher and higher energy states, because the lower energy states are already occupied. And higher energy states means higher kinetic energy. This creates a pressure, a quantum mechanical pressure that resists compression, that increases rapidly as the electrons are pushed closer together. This pressure has a precise mathematical form. It depends on the electron number density raised to the 5/3 power. As the density of electrons increases, the pressure rises steeply. The resistance to compression grows rapidly. And this quantum mechanical pressure, this Pauli pressure or degeneracy pressure, is what gives matter its solidity, its resistance to compression, its fundamental impermeability. It is worth emphasizing, again and with force, that this pressure has nothing to do with electromagnetic forces between the electrons. The electrons in your hand are not repelling the electrons in the wall through electromagnetic interaction. Or rather, electromagnetic repulsion plays a secondary role. The primary resistance comes from the Pauli Exclusion Principle, from the fundamental quantum mechanical prohibition on two fermions occupying the same state. The wall is solid not because of forces, but because of quantum statistics. There is a beautiful way to make this more concrete by thinking about what happens when you compress a collection of electrons, a metal, for instance, into a smaller volume. Metals contain enormous numbers of electrons that are free to move throughout the material, the so-called conduction electrons, detached from their parent atoms and able to roam freely through the metallic lattice. These electrons are fermions, subject to the Pauli Exclusion Principle, and they fill the available energy states from the bottom up, with at most two electrons, one spin up and one spin down in each state. The energy of the highest occupied state, the energy of the electron at the very top of this stack, is called the Fermi energy, named for Enrico Fermi. The Fermi energy is a property of the metal that depends on the density of conduction electrons. Copper has a Fermi energy of about 7 electron volts. Aluminium has a Fermi energy of about 11 electron volts. These energies correspond to electron velocities of about 1.5 million meters per second, a significant fraction of the speed of light, even at absolute zero temperature. This is remarkable. At absolute zero, a classical ideal gas would have zero kinetic energy. Every molecule would be at rest. But at absolute zero, a quantum mechanical system of fermions has an enormous amount of kinetic energy, the zero-point kinetic energy imposed by the Pauli Exclusion Principle. The electrons cannot all be at rest, because that would require them all to be in the same quantum state, which is forbidden. They must stack into higher energy states, and the result is a sea of electrons with a wide distribution of energies, all the way up to the Fermi energy. If you try to compress the metal, to reduce its volume while keeping the number of electrons fixed, the electron density increases. Higher density means more electrons squeezed into a smaller volume. By the Pauli Exclusion Principle, they must stack into higher energy states because the lower states are already full. The average energy per electron increases, the total energy of the electron gas increases, and the resistance to further compression, the quantum mechanical pressure, increases steeply. The resistance to compression of a material can be quantified as the bulk modulus, a measure of how much pressure is required to compress the material by a given fraction of its volume. For metals, a significant portion of the bulk modulus, the resistance to compression that makes metals hard and difficult to deform, comes from this quantum mechanical electron pressure, this Pauli degeneracy pressure. The same principle that prevents your hand from passing through a wall also makes steel hard and aluminium rigid. For magnesium, the contribution from electron degeneracy pressure alone gives a bulk modulus of about 64 gigapascals. The experimentally measured bulk modulus of magnesium is about 45 gigapascals. The agreement is remarkable for such a simple model. The quantum mechanics of fermions accounts for most of the hardness and rigidity of one of the most common structural metals. The Pauli Exclusion Principle does not stop at the scale of everyday matter. It reaches out into the cosmos, operating at the most extreme scales in the universe. When a star like the Sun exhausts its nuclear fuel, the outward pressure of radiation and thermal energy that has been supporting it against gravitational collapse disappears. The core of the star begins to collapse under its own gravity, but for stars in a certain mass range, the collapse is halted by the electron degeneracy pressure, the quantum mechanical pressure arising from the Pauli exclusion principle applied to the electrons in the stellar core. The result is a white dwarf, a stellar remnant approximately the mass of the Sun, compressed into a volume approximately the size of the Earth. The white dwarf is held up not by any ongoing nuclear reactions, but entirely by the Pauli pressure of its electrons. The electrons are packed so tightly that the Fermi energy is enormous. The kinetic energies of the electrons are relativistic, comparable to the rest mass energy of the electron itself. The maximum mass of a white dwarf, the mass above which electron degeneracy pressure can no longer hold up the star, is about 1 4/10 solar masses. This is the Chandrasekhar limit, named for the Indian physicist Subrahmanyan Chandrasekhar, who derived it in 1930 at the age of 19, while traveling by ship from India to England to begin his graduate studies. Above this limit, the electron degeneracy pressure is insufficient, and the stellar core collapses further into a neutron star if the mass is not too great, where neutron degeneracy pressure provides the support, or into a black hole if the mass is too great for even the neutrons to resist. The neutron star is the Pauli exclusion principle applied to neutrons rather than electrons. Neutrons, like electrons, are fermions. When the core of a sufficiently massive star collapses, the electrons and protons are forced together to form neutrons, releasing a flood of neutrinos. The resulting neutron star is held up by the degeneracy pressure of its neutrons, the same quantum statistical pressure that holds up the white dwarf, applied to a different species of fermion. A neutron star has a mass greater than the Sun compressed into a radius of about 10 kilometers, smaller than many cities. The Pauli exclusion principle is thus responsible not only for the solidity of everyday matter, but for the existence of white dwarfs and neutron stars, for the stability of two of the most extreme types of object in the observable universe. Without it, all matter would collapse under gravity, all stellar remnants would become black holes, and the universe would be a very different and far less habitable place. The contrast between fermions and bosons, between particles that obey the exclusion principle and particles that do not, leads to some of the most striking phenomena in physics. Difference in their quantum statistical behavior produces effects that are not just quantitative but qualitatively different. Bosons, because they are described by symmetric wave functions, have the opposite tendency to fermions. Where fermions avoid each other, where the antisymmetric wave function suppresses the probability of two fermions being in the same state, bosons tend to cluster together. The symmetric wave function enhances the probability of multiple bosons occupying the same state. In fact, the more bosons there are in a given state, the more likely additional bosons are to join them. This is the quantum statistical tendency, sometimes called bosonic bunching. This bunching tendency leads, at low temperatures, to a remarkable phenomenon called Bose-Einstein condensation. When a gas of bosons is cooled to a sufficiently low temperature, a macroscopic fraction of all the bosons simultaneously collapse into the ground state, the lowest available energy state. This sudden collective occupation of a single quantum state is called a Bose-Einstein condensate. In a Bose-Einstein condensate, all the particles in the macroscopic occupation of the ground state are described by the same wave function. They are, in a very real sense, all in the same place, not because they are physically coincident, but because their quantum states are identical. The condensate behaves as a single quantum object, with macroscopic quantum coherence, displaying quantum phenomena at the scale of millimeters or even centimeters rather than the scale of atoms. Laser light is a related phenomenon. In a laser, photons, which are bosons, are stimulated to occupy the same electromagnetic mode. The bosonic tendency to cluster together means that once some photons are in a given mode, additional photons are more likely to be emitted into that same mode. The result is a coherent beam of light in which all the photons are in exactly the same quantum state, the same direction, the same polarization, the same phase. Superfluidity, the phenomenon in which liquid helium at very low temperatures flows without any viscosity, without any resistance, through capillaries too narrow for ordinary fluids, is another boson effect. Helium-4 atoms are bosons, and at low temperatures they condense into a superfluid state governed by a single macroscopic wave function. These phenomena, Bose-Einstein condensation, laser light, superfluidity, superconductivity in many materials, are the bosonic counterparts of the fermionic phenomena we have been discussing. They all trace back to the same fundamental division of particles into two types, described by symmetric or antisymmetric wave functions, determined by whether the spin is integer or half-integer. The richness of physics, the existence of these extraordinary phenomena, is a consequence of this division. Let the quiet of this hour settle around you as the story nears its close. We have come a long way from the simple question of why you cannot walk through walls, from the particle in a box to the structure of atoms, from the periodic table to the hardness of metals, from white dwarf stars to the laser light in your phone. All of it traces back to one principle: no two fermions can occupy the same quantum state. This simple prohibition, derived from the antisymmetry requirement on the wave functions of identical half-integer spin particles, is the foundation on which the structure of matter rests. It is why electrons fill atomic shells in a specific order, producing the periodic table and the diversity of chemical elements. It is why atoms form molecules with specific geometries, producing the complexity of chemistry and the possibility of life. It is why metals are hard and rigid, resisting compression with a quantum mechanical pressure that has nothing to do with classical forces. It is why white dwarfs and neutron stars exist as stable remnants of stellar evolution rather than collapsing into black holes. And it is why your hand cannot pass through a wall, because the electrons in your hand cannot enter the quantum states already occupied by the electrons in the wall, and the energy required to push them into higher states creates an impenetrable quantum barrier. The universe is divided into two great categories of particle fermions and bosons. The fermions obey the exclusion principle and give rise to the structure and solidity of matter. The bosons do not obey it and give rise to the coherent, clustering phenomena of laser light and superfluidity and condensates. Both categories are essential. Both arise from the same mathematical framework, the requirement that identical particles be treated as indistinguishable, and the two ways in which a wave function can respond to particle exchange. Wolfgang Pauli saw the principle in the data before anyone understood why it was true. He inferred it from the patterns of light emitted and absorbed by atoms, from the structure of atomic energy levels revealed by spectroscopy. He did not have wave functions or the Schrödinger equation or the spin statistics theorem. He had spectra and physical intuition, and the willingness to follow the data to an unexpected conclusion. The principle was named for him and remains one of the cornerstones of modern physics. The history of quantum mechanics is in many ways a history of surprise, of predictions that seemed absurd and turned out to be correct, of principles that seemed arbitrary and turned out to be necessary, of phenomena that had no place in classical physics and turned out to be the foundation of the physical world. The Pauli Exclusion Principle was discovered in this spirit. In the years following the First World War, the central problem in atomic physics was understanding the structure of the atom. The Bohr model, introduced in 1913, had provided a first picture: electrons orbiting the nucleus in discrete circular orbits, each with a specific energy, with atoms emitting light when electrons jumped from higher orbits to lower ones. This model explained the hydrogen spectrum with impressive accuracy. But it struggled with atoms that had more than one electron, and it provided no explanation for the periodic table, for why elements with certain numbers of electrons had similar chemical properties. By the early 1920s, physicists had accumulated a large body of spectroscopic data, detailed measurements of the frequencies of light emitted and absorbed by atoms of different elements. This data encoded the structure of atomic energy levels, and careful analysis could reveal which quantum numbers characterized each level. The challenge was to find the principle that explained why electrons occupied the levels they did, rather than simply all falling into the lowest available state. This was the problem that Pauli attacked. Working through the data on atomic energy levels, Pauli noticed that each energy level in an atom could be characterized by a set of quantum numbers, and that the data was consistent with a single, simple rule: no two electrons in an atom could have the same complete set of quantum numbers. If the quantum numbers of a level were all identical for two electrons, one of them had to go somewhere else. The discovery required extraordinary care and precision in the analysis of spectroscopic data, the kind of meticulous, patient work that might seem unexciting, but that requires deep physical intuition to do well. Pauli was capable of both the careful analysis and the bold physical conclusion. His announcement of the exclusion principle in 1924 was immediately recognized by his colleagues as a fundamental result, even though the explanation, in terms of antisymmetric wave functions and the spin statistics theorem, was not yet available. Pauli was 24 years old when he announced the exclusion principle. He went on to make many other fundamental contributions to physics: the neutrino hypothesis, the derivation of the hydrogen spectrum from matrix mechanics, contributions to quantum field theory, and the spin statistics theorem itself. But the exclusion principle is his most lasting and most fundamental legacy. It is named for him, it is taught in every quantum mechanics course in the world, and it underlies a vast range of physical phenomena, from the structure of atoms to the stability of neutron stars. In 1945, Pauli was awarded the Nobel Prize in Physics for the discovery of the exclusion principle. He received the news while he was a professor in Princeton, having fled Europe during the Second World War. He had been in the United States since 1940, working at the Institute for Advanced Study, where Einstein was also a faculty member. Pauli and Einstein had a complex relationship. They respected each other deeply, but they disagreed about fundamental interpretations of quantum mechanics. Einstein never accepted the Copenhagen interpretation, the view that quantum mechanics gives only probabilistic predictions and that the wave function describes the complete reality of a quantum system. Pauli, by contrast, was one of the architects of the Copenhagen approach and had little patience for what he saw as Einstein's philosophical conservatism in the face of clear mathematical and experimental evidence. Their debates were intense and productive, the kind of intellectual confrontation between brilliant minds that often generates the most clarifying insights. And the context of their shared exile from a Europe consumed by war added a particular gravity to their conversations about the nature of physical reality. The structure of the periodic table is one of the great achievements of human understanding, a map of the elements organized by their atomic number, revealing deep regularities in chemical behavior that correspond to the filling of electronic shells. Understanding this structure requires the Pauli Exclusion Principle, the concept of quantum numbers, and the organization of electrons into shells and subshells. In a hydrogen atom, the electron is characterized by 4 quantum numbers. The principal quantum number n, which takes positive integer values and determines the overall energy of the electron. The angular momentum quantum number L, which takes values from 0 to n-1 and determines the shape of the electron's orbital. The magnetic quantum number M, which takes integer values from -L to +L and determines the orientation of the orbital. And the spin quantum number S, which can be either +1/2 or -1/2. The Pauli Exclusion Principle states that no 2 electrons in an atom can have the same values for all 4 of these quantum numbers simultaneously. Since spin can take 2 values, each spatial orbital, each combination of n, l, and m can hold exactly 2 electrons, one with spin up and one with spin down. For n equals 1, the only possible value of L is 0, and the only possible value of m is also 0. So there is one spatial orbital, and it can hold 2 electrons. The first shell holds 2 electrons. For n equals 2, L can be 0 or 1. For L equals 0, m is 0, 1 orbital. For L equals 1, m can be -1, 0, or +1, 3 orbitals. So there are 4 spatial orbitals in the second shell, each holding 2 electrons, for a total of 8 electrons. For n equals 3, the pattern continues, with 9 spatial orbitals and a maximum of 18 electrons. The elements fill these shells in order. Hydrogen has 1 electron in the n equals 1 shell. Helium has 2, filling the n equals 1 shell. Lithium has 3 2 in the first shell and 1 in the second. Neon has 10 2 in the first shell and 8 in the second, filling the second shell completely. Sodium has 11, the first 2 shells full, and 1 electron starting the third. The chemical properties of an element are determined primarily by the electrons in its outermost partially filled shell, the valence electrons. Elements with the same number of valence electrons have similar chemical properties. This is why the periodic table organizes elements into columns. Elements in the same column have the same number of valence electrons and therefore similar chemical behaviors. The alkali metals, lithium, sodium, potassium, each have 1 valence electron and react vigorously with water. The halogens, fluorine, chlorine, bromine, each lack 1 electron to fill their outer shell and are highly reactive. The noble gases, helium, neon, argon, have completely filled shells and are essentially inert. All of this, the organization of the periodic table, the chemical properties of the elements, the basis of chemistry, is a direct consequence of the Pauli Exclusion Principle. The principle determines how many electrons can fit in each energy level, and the energy level occupancy determines the chemical properties of the atom. The Pauli Exclusion Principle connects to one of the deepest and most philosophically rich areas of physics, the relationship between symmetry and physical law. Symmetry is one of the most powerful organizing principles in modern physics. A symmetry of a physical system is a transformation that leaves the system's behavior unchanged. Translations in space, rotations, reflections, the exchange of identical particles, these are all symmetries, and each one implies a conservation law. The symmetry of translation in space implies conservation of momentum. The symmetry of rotation implies conservation of angular momentum. The symmetry of time translation implies conservation of energy. These connections between symmetries and conservation laws, first articulated by the mathematician Emmy Noether in 1915, are among the most beautiful and powerful results in theoretical physics. The Pauli Exclusion Principle is connected to a symmetry, the symmetry of identical particle exchange. The requirement that the physics be unchanged when two identical particles are swapped, the requirement of indistinguishability, forces the wave function to be either symmetric or antisymmetric. And the spin statistics theorem tells us which particles with half-integer spin must have antisymmetric wave functions. The exclusion principle follows. This connection to symmetry means that the Pauli exclusion principle is not an ad hoc rule, not a constraint imposed from outside on the behavior of electrons. It is a consequence of the mathematics of quantum mechanics applied to identical particles, combined with the spin statistics theorem that comes from relativistic quantum field theory. It is, in other words, as deeply grounded in the foundations of physics as any result we have. The spin statistics theorem itself is one of the more technically challenging results in quantum field theory. It requires the full apparatus of relativistic quantum field theory, the Lorentz invariance of the theory, the positive energy requirement, the local commutativity of spacelike separated operators. These are not simple concepts. But the theorem that emerges from them is both simple and profound. All half-integer spin particles must be fermions, and all integer spin particles must be bosons. There are no exceptions. Every particle in the universe falls into one category or the other, and the category is determined by the spin. The profundity of this result is difficult to overstate. The spin of a particle, which determines how it transforms under rotations, a property of its geometry in the abstract mathematical space of quantum states, determines whether it clusters or avoids, whether it can share a state or not, whether it contributes to the structure of matter or to the coherence of radiation. Two seemingly unrelated properties, spin and statistical behavior, are connected by a deep mathematical theorem. The universe is more tightly constrained than it had any right to be, and the constraint produces the world we see. There is one more beautiful thread in this story, the connection between the Pauli exclusion principle and the arrow of time, the direction in which the universe evolves. The second law of thermodynamics states that the entropy of an isolated system never decreases, that physical processes always move in the direction of increasing disorder, increasing entropy. This is what gives time its arrow. The future is the direction of increasing entropy, and the past is the direction from which entropy was lower. The universe began in a state of very low entropy, the highly ordered, dense, hot state of the Big Bang, and has been expanding and increasing in entropy ever since. The Pauli exclusion principle is relevant to this story because it determines the maximum entropy that a system of fermions can achieve. When a collection of fermions is in its lowest energy state, when all the lowest energy levels are filled, with two fermions in each level and all higher levels empty, it is in a state of zero temperature and minimum entropy. This is the ground state of a fermion system. To increase the entropy of the system, you must excite fermions from their ground state levels to higher levels. In a metal at room temperature, the conduction electrons are almost all in their ground state configuration. The vast majority of the available quantum states below the Fermi energy are filled, and the vast majority above it are empty. Only the electrons very close to the Fermi energy are affected by the thermal energy of room temperature. The electrons deep below the Fermi energy are locked in their states by the Pauli exclusion principle. There are no available states for them to be excited into without a very large energy investment. This is why the specific heat of metals at low temperatures is much smaller than classical physics predicts. Classical physics would say that each conduction electron contributes to the heat capacity by absorbing thermal energy. But the Pauli exclusion principle locks most of the electrons into their ground state levels, where they cannot absorb heat. Only the electrons near the Fermi surface can be excited by thermal fluctuations. The result is a specific heat that is much smaller than classical predictions, and that grows linearly with temperature at low temperatures, in striking contrast to the constant specific heat that classical physics predicts. This was one of the early triumphs of quantum mechanics applied to metals, the explanation of the anomalously small specific heat of electrons, which had been a persistent puzzle since the late 19th century. The Pauli Exclusion Principle, applied to the electron gas in a metal, explained the anomaly with remarkable precision. The universe, in this sense, is structured by exclusion. The fermions that make up matter cannot all collapse into the same state. They are forbidden from it. They are forced by the mathematics of quantum mechanics to spread themselves across many different states, to maintain diversity, to resist homogenization. This resistance, this insistence on difference, is what gives matter its structure, its complexity, its capacity for the diversity of chemical behavior that makes life possible. And the bosons, with their tendency to cluster, give rise to the coherent phenomena of light and superfluidity, the unifying, clarifying, coherence-seeking aspects of the physical world. The universe is balanced between the diversity of fermions and the coherence of bosons, between the exclusion that gives matter structure and the clustering that gives rise to light. It is a beautiful balance. And it is the balance that makes the universe the kind of place it is. Among the most remarkable things about the Pauli Exclusion Principle is how it bridges scales, how a principle derived from the quantum mechanics of single electrons turns out to govern the behavior of macroscopic objects and astronomical objects alike. Consider the hardness of diamond. Diamond is the hardest naturally occurring material on Earth, capable of scratching any other material. Its hardness comes from the network of covalent bonds between carbon atoms in the diamond crystal structure. Each carbon atom is bonded to 4 others in a tetrahedral arrangement, and the strength of these bonds determines the hardness of the material. The strength of the bonds, in turn, comes from the electronic structure of carbon, from the fact that carbon has 4 valence electrons, each in a specific quantum state, available for bonding with neighboring atoms. The specificity of carbon's bonding, 4 bonds, tetrahedral geometry, is a direct consequence of the Pauli Exclusion Principle. Carbon has 6 electrons. 2 are in the innermost shell, with n equals 1, completely filling it. 4 are in the second shell, with n equals 2, partially filling it. These 4 outer electrons are the valence electrons. They can form 4 bonds with neighboring atoms, 1 for each valence electron. The geometry of these bonds, the tetrahedral arrangement that gives diamond its structure, is determined by the quantum mechanics of the carbon atom, which is in turn determined by the Pauli Exclusion Principle. Now consider a neutron star. A neutron star is the collapsed remnant of a massive star, with a mass of 1 to 2 times the mass of the Sun compressed into a sphere about 20 kilometers in diameter. The density at the center of a neutron star is so extreme that individual neutrons are almost touching. The spacing between neutrons is comparable to the size of the neutrons themselves. At this density, the neutron degeneracy pressure, the quantum mechanical pressure arising from the Pauli Exclusion Principle applied to neutrons, is the primary force holding the star against gravitational collapse. The maximum mass of a neutron star, the Tolman-Oppenheimer-Volkoff limit, is determined by the balance between neutron degeneracy pressure and gravity. When the mass exceeds this limit, gravity wins and the star collapses further into a black hole. The Tolman-Oppenheimer-Volkoff limit is approximately 2 to 3 solar masses, depending on the equation of state of dense nuclear matter. The same principle, the Pauli Exclusion Principle, determines the hardness of diamond and the maximum mass of a neutron star. The scales differ by approximately a factor of 10 to the 50, but the mathematics is the same. Fermions cannot share quantum states, and the pressure arising from this prohibition resists compression at every scale. This universality, the fact that the same quantum mechanical principle operates consistently from the atomic scale to the astronomical scale, is one of the most striking features of physics. It is a consequence of the fact that physics is the same everywhere and at every scale, that the same equations, the same principles, the same mathematics govern the behavior of matter from the smallest quantum to the largest structure. The Pauli Exclusion Principle does not know whether it is operating in a diamond or a neutron star. It simply operates at every scale with perfect mathematical precision. The life of the electrons in a metal, the quantum statistical behavior of the conduction electron gas, provides one of the most beautiful examples of quantum mechanics applied to a macroscopic system, and it connects the abstract formalism of wave functions and quantum numbers to the tangible, measurable properties of real materials. In most metals, the conduction electrons can be treated as a free electron gas, electrons moving through the metal lattice, interacting primarily with each other and the lattice through averaged effects, without being bound to specific atoms. This is a simplified model, but it captures the essential physics remarkably well. In this model, the electrons are treated as fermions in a three-dimensional box, the box being the metal sample. The energy states are the three-dimensional analog of the particle in a box, each state characterized by three quantum numbers, one for each dimension. The electrons fill these states from the bottom up, subject to the Pauli Exclusion Principle, with at most 2 electrons in each state. The filled states form a sphere in the three-dimensional space of quantum numbers, the Fermi sphere. The surface of the Fermi sphere, the boundary between filled and empty states, is the Fermi surface. The energy of electrons at the Fermi surface is the Fermi energy. The Fermi energy depends on the density of conduction electrons. For copper, with roughly 9 times 10 to the 28th electrons per cubic meter, the Fermi energy is about 7 electron volts. This corresponds to an electron velocity of about 1.6 million meters per second, more than 0.5% of the speed of light. At room temperature, the thermal energy is about 1/40th of an electron volt, tiny compared to the Fermi energy. The vast majority of the electron states are essentially unaffected by room temperature. This is why metals conduct electricity so well. When an electric field is applied to a metal, it pushes the electrons slightly, increasing the energy of those moving in one direction relative to those moving in the other. Only the electrons near the Fermi surface, those with enough energy to be affected by the tiny thermal fluctuations, can respond to the field. The others are locked in their states by the Pauli Exclusion Principle. But those near the Fermi surface can change their states easily, moving into the slightly higher energy states available above the Fermi energy. This gives rise to the electrical current. The fact that only electrons near the Fermi surface contribute to conduction also explains the linear temperature dependence of the specific heat of metals at low temperatures. Only the electrons within about kT of the Fermi surface, where K is Boltzmann's constant and T is temperature, can be thermally excited. The fraction of electrons that can be excited is proportional to T over the Fermi temperature. The thermal energy they absorb is also proportional to T, so the specific heat is proportional to T squared divided by T, which gives a linear temperature dependence. This linear temperature dependence of the electronic specific heat of metals is one of the most precise confirmations of the quantum statistical theory of electrons in metals. These quantitative predictions, the Fermi energy, the specific heat, the bulk modulus, all emerge from the same simple model, electrons in a box, subject to the Pauli Exclusion Principle. The model is simple, the predictions are quantitative, and the agreement with experiment is striking. This is quantum mechanics, at its most powerful, deriving macroscopic properties of real materials from first principles, using nothing but the wave function of a particle in a box, and the constraint that no 2 electrons can share the same quantum state. There is something deeply human about the way the Pauli Exclusion Principle operates in the natural world, and about the way it was discovered. It is a principle of individuality. It insists that every fermion must be distinct, that no 2 can be in exactly the same state, that each must have some characteristic that distinguishes it from every other. In a universe of identical particles, the exclusion principle enforces a kind of mathematical diversity, a requirement that the particles spread themselves out over the available quantum states rather than collapsing together into a single uniform state. This insistence on difference, this quantum mechanical prohibition on sameness, is what gives matter its structure. Without it, all electrons would collapse into the same state. All atoms would be identical spheres of uniform electron density. Chemistry would be impossible. Biological complexity would be unimaginable. The diversity of the chemical elements, the specificity of chemical bonding, the complexity of molecular structures, the precision of biological molecules, all of it depends on the exclusion principle's insistence that no two electrons can be the same. Pauli himself would probably have been amused or irritated by this anthropomorphic framing. He had little patience for what he considered unnecessary philosophical elaboration on clear mathematical facts, but the observation stands. The physical world has the diversity and complexity it does because the electrons that constitute it are forced, by a mathematical theorem about the symmetry of quantum states, to be distinct from one another. The bosons, by contrast, embrace sameness. They cluster together, occupy the same states willingly, produce the coherent phenomena of laser light and superfluidity and condensates. The universe is divided between these two tendencies, the fermionic insistence on individuality and the bosonic embrace of collectivity. And it is the tension between these two tendencies, between the structure imposed by fermions and the coherence enabled by bosons, that gives the universe its particular character. We are fermions, our bodies are made of quarks, which are fermions, and electrons, which are fermions, and their composite particles, which behave as fermions. The ground beneath us is held up by the Pauli pressure of electrons. The light by which we see is carried by photons, which are bosons, moving freely without exclusion through the electromagnetic field. We are structure held together by exclusion, illuminated by coherence. That is a beautiful thing to rest in at the end of this night. The universe is exactly what the mathematics says it should be, no more, no less. And in that mathematical precision, in the quiet certainty of the exclusion principle, operating at every scale, from the atom to the neutron star, there is something that feels, in the deepest sense, like home. The discovery of the spin statistics theorem, the deep result that connects the spin of a particle to its statistical behavior, is one of the great achievements of 20th century theoretical physics, and it deserves more attention than it typically receives in popular accounts of quantum mechanics. The spin statistics theorem was proved rigorously by Wolfgang Pauli himself in 1940, 16 years after he had announced the exclusion principle based on empirical evidence. The proof required the full framework of relativistic quantum field theory, a framework that had been under development throughout the 1930s and that combined quantum mechanics with Einstein's special relativity into a single consistent theory. The key ingredients of the proof are the requirements of Lorentz invariance, the requirement that the laws of physics look the same in all inertial reference frames as demanded by special relativity, and the requirement that the energy of the quantum field be positive, which ensures that the quantum vacuum is stable and that you cannot extract unlimited energy from it. Together, these requirements force the connection between spin and statistics. Half-integer spin particles must have antisymmetric wave functions and therefore obey the exclusion principle, while integer spin particles must have symmetric wave functions and therefore behave as bosons. The remarkable thing about the proof is that it connects two seemingly unrelated properties of particles, their geometric transformation properties under rotations, encoded in the spin, and their statistical behavior under particle exchange, encoded in the symmetry of the wave function. There is no obvious reason, from the perspective of classical physics or even elementary quantum mechanics, why these two properties should be related. The connection emerges only when you combine quantum mechanics with special relativity in a fully consistent framework. Richard Feynman, who spent much of his career thinking about how to explain quantum mechanics clearly and who was one of the architects of quantum electrodynamics, said in a lecture late in his life that the spin statistics theorem was one of the things in physics that he had never been able to explain without using advanced mathematics. He could derive it, he could verify it, he could explain its consequences. But he could not find a simple, intuitive explanation for why it had to be true. It was, for him, one of the deep mysterious facts about quantum mechanics that the theory demanded without providing an intuitive picture. This is characteristic of the deepest results in physics. They are not always intuitively obvious. They emerge from the mathematics, from the requirements of consistency between different theoretical frameworks, from the demand that the theory be free of internal contradictions, and they reveal a structure of the universe that is more tightly constrained, more internally consistent, more mathematically precise than any intuitive picture would suggest. The spin statistics theorem is one such result. It tells us that the universe is organized into exactly two categories of particle, distinguished by their spin, with everything else, their statistical behavior, the symmetry of their wave functions, whether they obey the exclusion principle, following necessarily. The two categories are complete, exhaustive, and mutually exclusive. There is no third option, no particle that is half fermion and half boson. The universe has been divided, cleanly and absolutely, into two types. This clean division, this binary classification of all particles in the universe, is one of the most striking organizational features of physics, and it has consequences at every scale, from the structure of atoms to the stability of neutron stars, from the hardness of diamond to the coherence of laser light. The simple binary distinction between fermion and boson, between exclusion and clustering, between antisymmetric and symmetric wave functions, generates the full diversity of physical phenomena that we observe. As the night holds you in its quiet, consider the full sweep of what the Pauli Exclusion Principle has given us. Not as an abstract principle, but as a physical reality, as the thing that makes the world feel the way it does. The solidness of a table, the resistance of a floor to your weight, the hardness of rock and metal, the fact that matter has volume and takes up space rather than being infinitely compressible. All of this, every solid surface you have ever touched, every object that has ever held its shape in your hands, is a manifestation of the Pauli Exclusion Principle. The electrons in solid matter resist compression not because of any force, but because of the mathematical impossibility of two fermions sharing a quantum state. The diversity of chemistry, the fact that carbon forms 4 bonds and hydrogen forms 1. The specific geometry of molecules, the tetrahedral shape of methane, the double helix of DNA, the precise folding of proteins. All of this is a consequence of the electronic structure of atoms, which is in turn a consequence of how electrons fill atomic orbitals under the constraint of the exclusion principle, the existence of complex life. The fact that biological molecules can have the specific structures they do, that enzymes can be precisely shaped to catalyze specific reactions, that DNA can encode information in a specific sequence of base pairs, that proteins can fold into specific three-dimensional shapes that perform specific functions. All of this depends on the chemical diversity that the Pauli Exclusion Principle makes possible. Without the exclusion principle, all atoms would be identical, all chemistry would be the same, and the molecular diversity of life would be impossible. The stability of stars and their remnants. The sun will eventually exhaust its nuclear fuel and collapse into a white dwarf, a stellar remnant held up by electron degeneracy pressure, by the Pauli exclusion principle applied to the electrons in the dense stellar core. More massive stars will collapse into neutron stars, held up by neutron degeneracy pressure, the same principle applied to neutrons. And if the mass is too great even for that, a black hole forms, the one outcome in which the Pauli exclusion principle cannot prevent collapse. The existence of the periodic table. The organization of matter into distinct chemical elements with specific properties. The fact that some elements are metals and some are non-metals, that some are reactive and some are inert, that elements fall into families with similar properties. All of this is encoded in the electronic structure of atoms, which is determined by the Pauli exclusion principle. Wolfgang Pauli, in his famous quote at the end of the lecture on quantum electrodynamics, from which the script for this episode was drawn, said that one should not rack one's brain about the problem of whether something one cannot know anything about exists. It was a typically acerbic comment about the limits of physical knowledge, a reminder that physics is about what can be measured, what can be tested, what can be verified. The exclusion principle is not something you can visualize directly. You cannot see the antisymmetry of a wave function. You cannot observe the quantum state directly. What you can observe are its consequences: the solidity of matter, the structure of atoms, the diversity of chemistry, the existence of white dwarf stars. And those consequences are everywhere, in everything, at every moment. You are resting on the Pauli exclusion principle right now. The floor beneath you, the air around you, the body you inhabit, all of it is structured by this one quantum mechanical rule. The universe is held together, in a very literal and precise sense, by the impossibility of two fermions sharing a state. That is the story of the Pauli exclusion principle. And it is, in its quiet way, one of the most beautiful stories in physics. Not dramatic, not explosive, not visible in the way that a black hole or a neutron star or a gamma-ray burst is visible. Just quiet, mathematical, absolute. The universe saying, without exception and without appeal, no two of you can be the same. One final thread before the story rests completely. The Pauli exclusion principle is not only about what fermions cannot do, it is also about what they can do and the richness of what is possible within the constraint. Consider the carbon atom. It has 6 electrons, 2 fill the innermost shell, constrained to the n equals 1 level, 4 fill the next shell, in the n equals 2 level. These 4 valence electrons can form bonds with other atoms in several different ways, depending on how the quantum states of the carbon atom hybridize in the presence of neighboring atoms. Carbon can form 4 single bonds, arranged tetrahedrally. This is what happens in diamond and in methane. It can form 2 single bonds and 1 double bond in a planar arrangement. This is what happens in ethylene and in the flat carbon sheets of graphene. It can form 1 single bond and 1 triple bond. This is what happens in acetylene. Each of these different bonding configurations involves different arrangements of the 4 valence electrons in different combinations of quantum states. The Pauli exclusion principle does not dictate which arrangement occurs. It simply rules out the impossible ones and defines the space of possible arrangements. Within that space, the quantum mechanics of the chemical bond determines which arrangement is most stable in a given molecular environment. This is what makes carbon the basis of life. Its ability to form 4 strong bonds in multiple different geometries gives it a chemical versatility unmatched by any other element. Carbon can form rings, chains, sheets, cages, helices, an effectively unlimited variety of molecular architectures. And all of this versatility is constrained and enabled by the Pauli exclusion principle, which allows 4 valence electrons to exist in distinct quantum states while forbidding a 5th valence electron from joining them. The richness of organic chemistry, the complexity of biological molecules, the diversity of pharmaceutical compounds, the variety of polymers and materials, is ultimately a consequence of the Pauli exclusion principle applied to carbon. Not a direct consequence, not a simple one, but a consequence nonetheless, mediated through the electronic structure of the carbon atom and the quantum mechanics of chemical bonding. We are carbon-based life forms. Our bodies are built of carbon-based molecules. The information encoded in our DNA is written in the language of carbon chemistry. And that chemistry, in all its richness and specificity and diversity, rests on the foundation of the Pauli Exclusion Principle, on the simple prohibition that no two electrons in a carbon atom can share the same quantum state. That prohibition is ancient. It has been operating since the first carbon atoms were forged in the cores of early stars, billions of years before the Earth existed. It will continue to operate long after the last carbon atom has decayed or been swallowed by a black hole. It is one of the permanent, immutable features of the mathematical structure of the universe, as certain and as final as 2 + 2 = 4. And tonight, you are one of its consequences. Lying still in the dark, made of carbon and other elements whose structure is determined by the exclusion principle, resting on a surface made solid by the same principle, breathing air whose molecules are held together by chemical bonds that the same principle enables. The universe has arranged itself, through the application of one mathematical rule, into something complex enough to lie down and breathe and wonder about the principles that made it possible. That is extraordinary. And it is worth carrying into sleep. There is a profound connection between the Pauli Exclusion Principle and the concept of identity, not in the philosophical sense, but in the precise mathematical sense that quantum mechanics demands. In classical physics, identical objects can still be distinguished by their positions. Two identical billiard balls are the same in every measurable property, but one is here and the other is there, and this spatial distinction is enough to tell them apart. Classical physics does not require any deeper concept of identity. The balls are where they are, and their positions tell you which is which. In quantum mechanics, this fails. A quantum particle does not have a definite position. It has a wave function, a probability distribution over positions spread through space. Two quantum particles of the same type, two electrons, say both have wave functions spread through the same region of space. There is no fact of the matter about which electron is at which position, because neither electron is at any definite position. The electrons are probability clouds, not billiard balls, and two overlapping probability clouds cannot be distinguished by their positions. This is why identical quantum particles are truly indistinguishable, in a way that identical classical objects are not. And this indistinguishability, this fundamental lack of any principle that would let you label one electron as number 1 and another as number 2, forces the wave function of a multi-electron system to reflect the symmetry or antisymmetry under exchange. The result is a kind of quantum democracy among identical particles. No electron can be more important than any other. No electron can claim a label, an identity, a position that distinguishes it from its identical partners. They are all waves in the same ocean, and the mathematics of quantum mechanics enforces this democracy absolutely through the requirement that the wave function be symmetric or antisymmetric under exchange. The Pauli Exclusion Principle emerges from this democracy. In a world where electrons cannot be distinguished, where no electron can claim a unique identity, the antisymmetry of the wave function ensures that no two electrons can be in exactly the same state. They must be different from each other, not because of any force, but because the mathematics of quantum mechanics denies them the possibility of sameness. This is, in a sense, the deepest statement of the exclusion principle. It is not a law about what electrons are forbidden to do. It is a consequence of what electrons fundamentally are indistinguishable quantum particles, described by antisymmetric wave functions, unable to claim individual identities and therefore unable to share states. The universe, at its deepest quantum level, does not allow electrons to be the same. They must differ always in at least one quantum number. This enforced diversity, this mathematical prohibition on sameness, is what gives matter its structure, its richness, its capacity for the complexity of chemistry and biology and mind. We are, in the end, consequences of the Pauli Exclusion Principle. The atoms in our bodies have the structures they do because of it. The molecules that carry our genetic information have the geometries they do because of it. The the neurons that process our thoughts, the proteins that catalyze our metabolism, the cells that make up our tissues, all of it rests on the foundation of this one quantum mechanical rule. No two electrons can be the same, and from that prohibition, the world is made. Before the story closes completely, there is a beautiful thought experiment worth dwelling on, one that connects the Pauli Exclusion Principle to one of the most fundamental questions in physics. Why is there something rather than nothing? The standard model of cosmology tells us that the universe began in a state of very high density and temperature, the Big Bang, and has been expanding and cooling ever since. In the earliest moments, the universe was a dense plasma of quarks, gluons, photons, and other particles, at temperatures so high that the particles were moving at nearly the speed of light. As the universe expanded and cooled, the quarks combined into protons and neutrons, which combined with electrons to form atoms, which combined to form molecules, which formed gas clouds, which collapsed under gravity to form stars. Throughout this history, the Pauli Exclusion Principle has been operating, preventing the quarks from all collapsing into the same state, preventing the electrons from all occupying the same atomic orbital, preventing matter from collapsing into a structureless soup of undifferentiated quantum states. If there were no Pauli Exclusion Principle, if all particles were bosons rather than some being fermions, then in the cooling aftermath of the Big Bang, all the matter particles would tend to collapse into the lowest available energy state. There would be no atomic shells, no chemical diversity, no periodic table. There would be a universe of structureless matter, all in the same quantum state, with no chemistry and no complexity. The existence of the Pauli Exclusion Principle, the fact that matter is made of fermions rather than bosons, is thus a precondition for the existence of a complex universe. Not just a universe that contains life, but a universe that contains any structure at all. The diversity of the natural world, from the periodic table to the diversity of species, traces back to this one quantum statistical fact. This is one of the places where physics touches on the deepest questions of existence. Why is the universe structured the way it is? Why does it have the laws it has? Why are matter particles fermions rather than bosons? Physics cannot answer these questions. They lie outside the domain of what physics can address, but physics can trace the consequences. And the consequence of matter being fermionic, of the Pauli Exclusion Principle holding, is the existence of everything we see around us. The universe is the way it is, at least in part, because no two fermions can share a quantum state. That is the Pauli Exclusion Principle. And it is one of the most fundamental and most consequential facts about the physical world. Rest in that tonight. You are here, complex, conscious, aware, because the universe has this property, because electrons cannot share quantum states, because the wave function must be antisymmetric, because spin and statistics are connected by a deep theorem of relativistic quantum field theory. You are here because of a mathematical rule about the symmetry of wave functions. And that is, in its quiet way, one of the most astonishing things about your existence. Let your breathing slow. Let that thought soften into the background. The Pauli Exclusion Principle will keep operating while you sleep, in the floor beneath you, in the walls around you, in the atoms of your body, in every electron in the universe. It does not rest. It does not pause. It is simply the way things are, always and without exception. And in that constancy, in the quiet, absolute, mathematical certainty of the exclusion principle, there is a kind of peace. Sleep well. The universe is holding you up. The physicist Paul Dirac, one of the architects of quantum mechanics and quantum field theory, said that the laws of physics should be beautiful. He meant this not as a metaphysical claim, but as a practical guide to theoretical physics. That the correct theory would have a mathematical elegance, a simplicity and inevitability that would mark it as fundamentally true rather than merely approximately correct. Dirac himself made his greatest discoveries by following this aesthetic principle, by insisting that the equations of quantum mechanics be compatible with special relativity, even when the resulting mathematics seemed bizarre, and arriving at the prediction of antimatter as a consequence. The Pauli Exclusion Principle satisfies Dirac's criterion. It is beautiful not in a superficial sense, but in the deep sense that it is inevitable. Once you accept the framework of quantum mechanics and the indistinguishability of identical particles, it follows with mathematical necessity. You cannot have quantum mechanics and identical particles without getting either symmetric or antisymmetric wave functions. You cannot have relativistic quantum field theory without getting the spin statistics connection. And once you have the spin statistics connection, the exclusion principle for half-integer spin particles follows immediately. The principle is also economical in the mathematical sense. It is a single constraint that gives rise to an enormous range of consequences. From one prohibition, no two fermions in the same state, you get atomic structure, the periodic table, chemical bonding, the hardness of solids, the stability of white dwarfs and neutron stars, the specific heat of metals, and the impossibility of walking through walls. The ratio of consequences to assumptions is extraordinary. One rule, applied consistently, generates the structure of the physical world. This economy, this extraordinary productivity of a single simple principle, is one of the hallmarks of a deep physical law. The great laws of physics are not complicated. Newton's law of gravitation is a simple inverse square. Maxwell's equations, when written in their most compact form, are four beautiful symmetrical equations. Einstein's field equations are compact and elegant. The Schrödinger equation is a single partial differential equation, and the Pauli exclusion principle is a single statement about the symmetry of wave functions. The universe runs on simple principles, applied universally and consistently, giving rise through their interaction to the enormous complexity we observe. The Pauli exclusion principle is one of those principles. And its consequences, traced through the levels of physical organization from the quantum to the cosmic, are among the most important facts about the world we live in. Wolfgang Pauli would probably have found it fitting that a principle he deduced from atomic spectra in 1924 turned out to be the foundation of the solidity of matter, the organization of chemistry, and the stability of stellar remnants. He was a physicist of the first order, demanding, precise, uncomfortable with sloppy thinking, and the clarity and precision of the exclusion principle reflected his own intellectual character. The principle is clean, unambiguous, absolute. It admits no exceptions, no approximations, no edge cases. It simply is what it is, everywhere and always, without qualification. And everything we know, everything we can touch or see or inhabit, rests on it. That is worth knowing. And now, knowing it, you can rest. As we come to the end of our journey tonight, the story can begin to settle around you. We have traveled from a single particle in a box, through the profound consequence of particle indistinguishability, through the division of all matter into fermions and bosons, through the Pauli exclusion principle and its consequences for atomic structure and the periodic table, through the hardness of metals and the existence of neutron stars, and back to the simple everyday observation that the world is solid and that matter holds its shape. There is no need to hold any of that tightly now. You can let the details soften into impressions. The image of electrons stacking into higher and higher energy levels, each one forbidden by the exclusion principle from occupying a state already claimed. The image of the periodic table as a map of quantum exclusion, each element defined by how its electrons fill the available quantum states. The image of your hand approaching the wall and the quantum barrier that forms not from any force, but from the mathematical impossibility of two fermions sharing a state. Let these images drift through your awareness and dissolve, like waves on a quiet shore. The world is solid because of quantum mechanics. The floor holds you up because of the Pauli exclusion principle. The atoms in your body have the structure they do, the shells, the valence electrons, the chemical bonds, because of the simple prohibition on two identical fermions occupying the same quantum state. And the most extreme objects in the universe, white dwarf stars, neutron stars, are held up against gravitational collapse by the same principle applied at cosmic scales. The universe is governed at every scale from the atomic to the stellar by principles of extraordinary elegance and generality. The Pauli Exclusion Principle is one of them. And tonight, lying still in the dark, you are resting on a floor made solid by quantum mechanics, in a body made possible by atomic structure, in a universe shaped by the simple fact that no two fermions can ever be in the same place at the same time. Let your breathing slow. Let your body settle into wherever it is. The universe will keep unfolding on its own, just as it always has, steady, patient, and kind. Sleep well. Good night. Still drifting, let the rain take over from here. Close your eyes and let it wash everything away.